Нормально будет, да? Да. Так я понял, что сделал просто.
Okay, we continue with the talk of Andrei Yurievich Vesnin from the Sobolev Institute of Mathematics in Novosibirsk. He will speak about invariants of spatial graphs and corresponding nodes and links.
Yeah, thank you very much. Thank you very much to organize this, to opportunity to give a talk, and to opportunity to congratulate Sabir M. And in this rainy day, I prepared more sunny photo. It was in Sochi, a conference devoted to geometry and topology of three-dimensional manifolds with Sabir M. which is the first line, you see. So let me start from geometry and topology of three manifolds and explain why complete graphs are interesting in this context. So this is outline of my talk. So let me start from three manifolds. And there is a very famous presentation of three-dimensional manifolds as Higger splitting. So you take two handle body and you glue them along a boundary and you obtain manifold. And in this context, it was a definition of maximally symmetric manifolds in respect to Higger splitting. It was introduced by Bruno Zimmermann, and we say that closed orientable three-dimensional manifold is maximally symmetric if it has a Higger splitting of some genus which is bigger than 1, and find a group of orientation preserving homeomorphism of maximal possible order 12 times G minus 1, such that handle body are preserved by this group action. So this is a kind of equivalent group acting on handle body splitting. And there are many examples of such maximally symmetric manifolds. And the general theorem was proved in 1995 by Bruno Zimmermann, and he characterized these maximally symmetric free manifolds in the following way. So M is maximally symmetric free manifolds if and only if it is a finite regular cover of the following obifold. So obifold has three parameters. So firstly, the line space of the obifold is three-dimensional sphere, and sigma is just a free-string break on three strings, and M and N are singularity of equal to 2, 3, 4, or 5, and 3 is fixed, and for other arcs which don't mention singularity, always 2. So this is exactly the order of corresponding group, isotopy group. So such obifolds appear in this context, and you see the singular set is a graph with four vertices embedded into a three-dimensional sphere. And one of the most interesting example is the smallest volume hyperbolic orientable closed manifold M1 with volume about 0.94, and this manifold was recognized by computers independently by Jeffrey Weeks and Anatoly Timorovich Fomenko and Sergei Ilyich Matveyev, and for many years it was just the smallest known manifold, and after some years Gabay, Meyerhoff, and Miri proved that there are no smaller manifolds. So now we have a proof that this is the smallest one. And it is interesting that this manifold was considered by different authors with different covering properties when investigated, and in particular we know that this manifold is maximally symmetric with a genus equal to 2, Higari genus equal to 2, and G is an isometry group of this manifold. Is a hyperbolic isometries, and all of this group is equal to 12. And the corresponding singular set of the quotient over obifold is the four-vertex graph in three-dimensional sphere, and free-string break is exactly C2 in degree 3, C1 in degree minus 1 times C2. You see the picture here, and both parameters M and N are equal to 1. So in this context, it is interesting to understand the following question: how we can distinguish two graphs in three-dimensional sphere, and what kind of invariant we can use, and how these invariants are related to nodes and links which are can be found inside such graphs. And let me recall a little bit about classical node theory and Jones polynomial. So I suppose this stuff is known, but I recall we have a very nice theorem due to Kurt Rademeister, proved in 1927, and this theorem admits to consider ambient isotopy between two nodes as a sequence of Rademacher moves. So we can see the diagrams of nodes, and you can see the small paths, and you can see the three types of such moves as presented here. So red is just a part of the node diagram, and we consider this Rademacher move number 1, number 2, and number 3. And what Rademacher proved, that two nodes in three-dimensional sphere are ambient isotopy. If you don't leave, you can start from diagram of one of node and to arrive to the diagram of another node using finite sequence of moves among these three Rademacher moves and plane isotopy. And this approach admits to construct many invariants if you just consider diagrams of the nodes. And one of such invariant is related to the Jones polynomial, and if you say a few words about it. So let us start from diagram description of the node, and let us consider two splits. So we have a local situation as drawn on the left. We have crossing Z. And according to the local picture, we can denote regions by A and by B. So if you go from the crossing to the border of this circle, to the border of the disk, so on the left always region A, on the right region B. So we can see the two kinds of splits. So we remove crossing and consider the channel between A regions, or another possibility, you can see the channel between B regions. So you can apply these two splits, and suppose we have and crossing in our diagram, so we can apply one of these possible splits for crossing. So you'll get something on the plane which you call state, and this will be just a collection of disjoint closed curves. And for any state, we can arrive using A as number of A splits and B as number of B splits, and also we count number of connected components, denoted by model S. And after that, we can try to construct some invariants, and it's my pleasure to recall that firstly such kind of coloring in color A and B was considered by Johann Benedict in his book Primary Sizes of Topology, published in the middle of 19th century, but he constructed some polynomials, but these polynomials were not invariants. So, but nevertheless he constructed something. And using a little bit more clever approach, we can consider the bracket polynomial. So it considers some or all possible states of our diagram, and we just remember how many times we applied A channel, how many times we applied B channel, and how many connected components we obtained. And here are just a small example. So let's consider the diagram of the very famous node trefoil. So according to coloring in A and B, we have such a coloring on the left, and on the right there is one possible state. So what we did, we applied A channel, B channel, and again B channel. So we applied twice B channel, and we obtained two connected components. So this state gives us product A, B square, D square. And you can do it for any possible states, and finally we'll get a polynomial like this one. So it's called bracket polynomial just because it's denoted by brackets. But this is just the initial polynomial, and you want to obtain the invariant under Rademacher moves. So to do it, we consider the following properties. We consider when it will be invariant under Rademacher moves, and we arrive to result that B should be A inverse, and D should be minus A squared plus A minus 2. With these conditions, it will be invariant under Rademacher moves, number 2 and number 3. But it's still not invariant under first Rademacher move. And to make an invariant under first Rademacher move, we consider so-called Tauride number of a diagram. So we have crossings, and each crossing we have local orientation. So if you have picture like on the left, so we consider this positive crossing is suppose epsilon depending of crossing equal to +1. And on the right we have negative crossing, so suppose -1. And after that, you consider our diagram, and just take all crossings and summarize this weight. It's called a Tourist number. And finally, we get the following theorem. This approach due to Luke Kaufman. He considered this construction, and he proved that polynomial in A, this kind of Laurent polynomial, constructed in this way. So we have minus a cube in degree minus this number. We have bracket polynomial D, and we have a denominator just to normalize this value to obtain value 1 to trivial knot. So he proved this invariant of a knot under ambient isotopy. And it was 2 years later after famous Vaughan-Jones paper, and Vaughan-Jones used another approach, but this simple approach to Kaufman gives us the same Jones polynomial, just up to some change of variable. So if you take t equal minus 4, so you obtain polynomial depending on t. It is exactly classical Jones polynomial. So for which he obtained the Fields medal. So we know how it works for nodes. And now let us consider the situation when you have a special graph. So embedding graph in three-dimensional space. So we consider a graph with V vertices and E edges, and also we admit loops and multi-edges. So we consider this graph and we try to embed it three-dimensional space. So the result of embedding we call it special graph. And in particular case, if you consider graph, and if in the graph there is some cycle in the graph, so this cycle will be embedded as a node. And if you have two disjoint cycle, so this pair of cycle will be embedded as a link. And studying of embedding of graphs is natural extension of node theory. And let us do it. And let's remark that we work in precise linear category. And we define when two special graphs of equivalent. So we say that they're equivalent if there is ambient isotopy of the sphere which send one to another one. So similar to nodes, exactly. Okay. And again, we have a lot of special graphs around, and I would like to mention about very recent last year paper in the Journal of Protein Science, where you can see proteins on the left, and in the middle we have some graphs embedded in the space. So you see always you have a red edge, a green edge, and blue edge. So these two edges connect two vertices. So if you consider as a graph, it's just very simple graph with two vertices and three edges. But it can be embedded to the space in different way. So we need to understand not only combinatorial structure, but also topological property. So this a group of people they consider proteins and also consider nodes related to proteins and theta graphs related to proteins. And okay. So now in graph we have also vertices. So we need to care about vertices in our diagrams. And the following theorem was proved independently by Luke Kaufman and H.S.E. Yamada in the same year, in 1999. And they proved that two special graphs are ambient isotopic if and only if you can come from diagram of one to diagram of other using this finite sequence of moves among the three previous moves, and then the additional moves related to points of graphs. That's called random isotope. Now if you want to construct embedded, so you can use this reflexive moves and you can work with diagrams. And idea is due to H.S.E. Yamada. So let's consider the diagram of a graph. And suppose we have some crossing. So I mean double point of our projection. So now we apply free summations. They call it C plus, C minus, or C0. So we consider channel vertical type, channel of horizontal type, and the move S0 means we create a new vertex in this place. So we after splitting, we will get state, and now state is just a graph in a plane, and this graph can have more vertices than our original graph, because some vertices can appear with a zero transformation. So what we have now, we started from a graph in the space, and we got a collection of graphs on the plane. So we need to apply some invariance for these plane graphs, and it was done by Yamada, and he defined a polynomial which he knows by H. Firstly, for combinatorial graph, for an abstract graph, you just need to know vertices and connection between them. And what we use is the following. We use the number of connected components denoted by omega, and also use the first number, which is just number of edges minus number of vertices plus number of connected components. All these characteristics are combinatorial. This is dependent topology, and we define the following invariant. So we start with a graph, and we construct invariant H for our graph invariable A. So we take sum over all subsets of the set of edges, and we take -1 in degree of number of components of the new graph. So we take G and we delete F edges. So number of edges is the same, but number of edges is different. And then we multiply
the expression -1, -2, -1 inverse in degree, which is the number of corresponding graphs with some removed edges. So this is the invariant of the graph, and after that
we consider our states. So we start with a diagram. We applied 3 types of splittings. If there are n crossings, so we have 3 in degree n possibilities for our states. And again, similar to situation with the nodes, we consider parameters. So number m1, depending on our states, say how many times we applied S1 as plus split. M2 say us how many times we applied as minus split, and all other splits are just zero splits. And now Yamada polynomial of a special graph, we define it from his diagram. So what we do, so we consider the sum over all. Okay, I cannot show so, yeah. So I will consider A in degree number of in degree -1, -2. So it's remember how we arrive it to the state, and for the given state we apply
polynomial H, which is just for a third graph. So we obtain something
which is the Laurent polynomial in variable A, which is constructed for a diagram. It was suggested by Yamada, and he proved the following very nice theorem. So if we have 2 diagrams which are equivalent under randomizer moves from 1 to 5, then corresponding polynomial invariants are equal up to multiply -1 in some degree, integer degree k. But we have also 6 moves, so for 6 moves, randomizer move, we have the following statement. If you have 2 diagrams of special graph with maximal degree at most 3, so degree is just valency of vertex. So all vertices are of valency 2 or 3. So these 2 diagrams are equivalent under randomizer moves from 1 to 6. If they're equivalent, then corresponding polynomial are equal up to multiply -a in degree k for some integer k. So it gives us a polynomial invariance for graphs now. In particular, if you graph just circles, you obtain a polynomial for a node. So for nowadays, this Yamada polynomial is one of the most useful in this theory. It's quite strong. And for example, people who are working in the proteins also apply this polynomial to distinguish their special graphs. And some property of this polynomial can be studied. And for example, with my Chinese colleague, we studied properties of this Yamada polynomial, just a polynomial. So we asked what kind of zeros can appear. And we proved that if you consider all special graphs, so the set of zeros of a Yamada polynomial is dense in the complex plane. So you cannot restrict by some reasons. And our proof was constructive. So we just constructed 3 parameters within the family of special graph with such a property. Okay. And what I'm going to discuss is nodes and graph in special complete, nodes and links in special complete graphs. So this is a very nice result, all the results proved by John Conway, Cameron Gordon, and independently by Gernot Sachs. So if our graph is big enough as a graph, so it always contains some nodes or links in the following sense. So suppose our graph is just complete graph with n vertices. So it has n times n minus 1 divided by 2 edges. So very many. And Conway and Gordon and independently Sachs for case K6 proves that, so okay, if you have a complete graph on 6 vertices, and if you embed it in the three-dimensional sphere, there are always a pair of cycles which you form on a splittable two-component link. So you always find a link. And similar result if you have embedding of K7, so you always find a cycle which give you non-trivial node in the embedding. So we always something not to link it. Of course, if your graph is bigger than this one, so it also contains nodes and links. Similar results we obtained for another kind of graphs, so for example, for bipartite graphs, but they're not presented here. So just one picture for K6. So on the left you have some kind of diagram for K6 with 6 vertices, and among these triangles, I mean you can see the triangle cycles, you can easily find one black and one red which are really linked. So it's just example, but the theorem says that for any embedding you can do it. Okay. And in the case of Sachs, you see that he considers this property as special Alf-Kartovsky theorem about planar graphs. So we are interested in complete graphs. Also we are interested in more exactly in graph with 4 vertices, because we have interesting. Okay. In a property of three-dimensional manifolds related to maximal symmetry. So what we have if we consider graph with 4 vertices. So we have graph itself, and inside this graph we have 7 cycles. So they formed by cycles in the graph. And so if you consider embedding of the graph K4 in three-dimensional space, we'll get also 7 nodes. And there is a very nice result proved by Yamamoto. So suppose we have these 7 cycles. So for any ordered 7 type of nodes, so you just choose nodes K1, K7, there exists such a special embedding of K4 that these nodes will be realized by these cycles. So it can be complicated as you want. So you can think about arbitrary nodes in your embedding. And at the same time, these 7 nodes don't determine the embedding of K4. So similar to nodes, people try to tabulate special graphs, and this is just initial list. It was done by Jonathan Simon in his paper devoted to study of topological properties of chemical structures. So there are diagrams of K4, embedding of K4 with the at most crossing in the diagram. So you can see that there are some nodes that appear as a trefoil, as a figured node, but not too many because we restricted number of crossings by 4. Okay. And we have a graph and Yamada polynomial, and also we have cycles, and you can calculate the Jones polynomial for corresponding nodes. So I would like to discuss the relation between polynomials of graphs and polynomial of nodes. And we consider not only Yamada polynomial, but also polynomial introduced by Zade in 1997. This polynomial also can be constructed from a diagram, and we denote by J. And I don't want to go to the original definition, and I use only the following result proved by Karim and Hyo last year. Then you can express a Zade polynomial via Yamada polynomial and some combinatorial parameter of a graph. More exactly, the lemma is the following. If you have planar graph with V vertices and E edges, and you have a diagram. Then the polynomial for this diagram is Yamada polynomial with variable a in degree 4, and divided by minus a square plus a minus 2 in degree number edges minus number vertices plus 1. So since I'm interested in AK4, so K4 is a planar graph, and it has 6 edges and 6 vertices, so it will be just expression in degree 3. Okay, so we will use the polynomial for our considerations. It's a little bit more convenient than Yamada, but it's just normalization of Yamada. And what we do is the following. So suppose we have a graph K4 embedded to this space. So we have edges, but now instead of edges, just take bands and draw corresponding the band corresponding to embedding of edges. And in this picture, this schematic picture, you have 4 vertices which are in red. These 4 vertices of our graph. We have black edges of our graph, and blue just boundaries of bands which we use it to construct some surface. So we started from graph in 3-dimensional space, and we can consider the surface, which will be topologically just a free-punctured disk embedded to the 3-dimensional sphere, and this surface has boundary components. You see they're drawn in blue, so you'll get 4 boundary components, and they form a link, which is just a boundary of our surface, and it will be a 4-component link. It's pointing to our bane of the graph. And now what we will do, we have a surface embedded to the sphere, so we can consider the ciphered form. More exactly, let us consider the surface. Suppose we have 2 classes of curves in our surface. So what we do, we just push one of the curve a little bit amount of our surface, so denoted by x plus. So now we have 2 curves in the 3-dimensional space, one x plus and one is y. So let's denote the function from the product of homology groups to integers, such that product of these 2 classes just a linking number of a curve which represents these classes. So just usual linking number, and you will get some ciphered form defined for product of homology groups, and this form will be important for us for discussion graphs. And we are based on the following theorem, proved by Kaufman, Simon, Walcott, and Zhao in 1903. They considered this ciphered form corresponding to spatial graphs, and they proved the following. Suppose we have a graph G, which is connected, frivalent, planar, with in edges. And this planet have a plane embedding. Suppose this plane embedding is prime in respect to some connected sum operation, which I don't want to discuss now. It's a very natural operation, but not now. So, okay, there are two statements. First statement, if number of edges is not more than 6, then for each embedding of our graph, there exists unique up to ambient isotopy surface with 0 ciphered form. So if you consider the surface correspond to the graph, you have some freedom. You can rotate your band around the edge of the graph. So they prove that you always can get the 0 ciphered form. And if number of edges is big, more than 6, so they say that there is an embedding of the graph is such a surface. For the 20 corresponding surface, the ciphered form will be non-zero. And if there exists such a 0 surface, then it is unique up to ambient isotopy. And our graph, which we are interested in, K4, it's a trivalent planar with 6 edges, so this maximal graph to which we apply the case 1. So let's do it. So what we want, we can associate 0 ciphered form surface to our embedding. And we can do it starting with initial information. So we have 6 H denoted by AI on the previous picture. Oops. So here the H A1 is 6. So we can see the crossings between them and count some numbers which denoted by W. Just can you help me? Can I go here? Oh, it's too much. Thank you. Okay, so we can see this is HAI, and again you can see the crossings between AI and J, and we denote the result by WIJ. And to obtain zero Seyfert form, we do the following. So we count the numbers n1 and 6, which depend on this WIJ according to this equation. And after that, we apply additional twists. So we have six segments of bands, and according to this n1 and 6, we apply half twists. So positive half twist, number 2 drawn on the right and -2 drawn on the left. So just we found these numbers and we applied corresponding number of half twists, and after that we will get a surface with zero Seyfert form. So we started from initial embedding. After that we corrected by using half twists of bands. Okay, and what we consider is a link obtained by this half twist. This link, now calligraphic L, is a bound of our surface, but after some half twist moves. And this is boundary of surface with zero Seyfert form, and we call it associated link for our diagram. So we construct for our graph surface, and after that we modify surface to make it zero Seyfert form, and after that we consider a boundary of this surface. And also we a little bit correct our polynomials. So instead of JJ, we consider JJ tilde, and what we do, we take variable minus a in degree 4 and consider in degree of the sum of all these additional half twists. So this is J tilde. It will be interesting for us. So we obtain some polynomial, Laurent polynomial in degree A, which constructed for embedding of K form. And the result which we proved in joint paper with my student Olga Ashmarina, it appeared just last month as Sbornik Mathematics. So first result is this new modified Jaget polynomial is invariant of the special embedding. After this modification, it is invariant. And after that, we consider how this polynomial is related to John's polynomials of objects related to our graph. So we have a graph, K4, we have 4 vertices and 6 edges. We already discussed it, that in this graph we have 7 cycles, so you give us 7 nodes, K1, K7. And else there are subgraphs. So how they appear? You just remove one of each, and you will get a graph with 2 vertices and 3 edges, like drawn the last line. And usually they call it theta graph just because they look similar to the Greek letter theta, 2 vertices connected by 3 edges. So we have original special graph K4, we have cycles which give us nodes, and we have subgraph which give us as a subgraph embedded to the space. And for nodes we can consider John's polynomial, and for graph we can consider modified Jaget polynomial. And we found the following relation between all these objects. So we start with the embedding of K4, and we have associated link L, which was constructed as a boundary of a modified surface with zero Seifert form. It has 4 components. It's calligraphic area. Also, we have 6 subgraphs denoted by theta 1, theta 6. And also, we have 7 nodes, which are embedding of cycles of our graph. And we have the following relation between invariants of these graphs and the nodes. So we have J tilde, this is modified Jaget polynomial. So we consider as modification of Yamada polynomial. And V is just a classical Jones polynomial. Take it with variable A. And small phi is just expression A squared plus A minus 2. So for any embedding of our K4, we have such expression. And also for the right part, you can consider not just graphs, but also for theta graph, you can consider associated links and nodes. So you can rewrite this expression the following way. So again, what we have K4, and we have a Jaget polynomial on the left. And on the right, you have Jones polynomial for associated link, which is 4 component and constructed for as a boundary of surface with 0 Seifert form. After that, you consider 6 links with 3 components which are associated to theta subgraphs of our original graph. And also we have 7 2-component links. So before it was just 7 nodes, but now we can see the cablings of links corresponding to twisted parameters. So they became two component links. So on the left we have Jaget polynomial for a special graph, and on the right we have only Jones polynomial. Jones polynomial of link is 4 components, or with 3, or with 2, which depend on our embedding. Okay, and I'm not going to present the proof because it's too technical, so just general idea. And finally, maybe I illustrate an example how this polynomials looks, and just one of example. So you can let us consider a special graph of such form, which was denoted by omega 7 in our tables. So we can find a normalized Jaget polynomial. It looks like this one. So we have phi in cube and also polynomial in variable A from degree theta 2 to minus theta 2. So after that, we calculate twisting parameters. So we consider this arcs from I to A6. You can see how they crossing, and consider sum of crossings, numbers of crossings. So we calculate that n1 equal minus 1 and n4 equal 1 and all other equal to 0. So we will need to apply additional twists. And our associated link for this diagram will be the following. So it has 4 components in blue, red, orange, and green. And you see the green and orange has additional twisting, and also blue and red has additional twists, each because of our parameters. So this is associated link. So this link is invariant of our special graph because this is a boundary of the surface with 0 Seifert form. And we can calculate the Jones polynomial. It's printed here. And tomorrow we can recognize that this node is hyperbolic. So its volume, which is equal to 18 plus something, is the invariant of this link. And so this is invariant of our graph. You can use hyperbolic geometry to construct invariants. Okay, now we go to theta subgraphs. So we have 3 types of them. So the theta subgraph theta 1, theta subgraph theta 4, they look like this one. And all other subgraphs are equivalent to trivial. So again, we calculate all these polynomials. Jaget polynomials with tilde, you'll get such expression. And after that, we need to find polynomial for 7 nodes. And this this graph is not not complicated, so there are consistent node, just figure-8 node and trivial. So for figure-8 node, we get Auger polynomial like presented on the first line, and for remaining which are trivial, we get Auger polynomial like this one. And okay, so we obtained all ingredients for our formula. So our theorem states that there is a following relation. So on the left, you have Auger polynomial for K4 minus the Jones polynomial for associated link, and on the left, you have invariant for other ingredients, for subgraphs and subnodes. So this typical result. So it's explaining you that you can consider Yamada polynomial for this particular class of graphs as a kind of version of linear combination of Jones polynomials. And since we have a lot of software to calculate Jones polynomial, you can use for this reason this formula. And as I already told, this situation is maximal possible. So I mean, we cannot apply this approach if number of edges is more than 6, because of Kaufman and other people's theorem. Just a second. Let me go back to this theorem. Okay, so because of this theorem, we can construct surface which are unique after isotopy only if our graph is planar, prevalent is with at most 6 edges. Unfortunately, for other more complicated graph, we can't use this machinery. And for a simpler graph, for theta graph, a similar result was obtained by He, about whom I already mentioned. His paper was published in last year in discrete mathematics. Okay, thank you. No, it's not the last slide. Thank you very much for your attention.
Thank you very much. Are there any questions?
Andrei, since you are able to express the Auger polynomial in terms of Jones polynomial, yes, is it possible to extend this expression for colored Jones polynomials?
So you need to define some kind of colored version of Auger or Yamada.
Is it possible or not?
In principle, it can be possible, just it's very technical, because you see the construction of colored Jones polynomial is very complicated. Okay, we are thinking in a little bit different direction. We would like to use another description of Jones polynomial, for example, via quantum groups, and consider something similar for Yamada or Auger. So with my students, we're trying to go in this direction now. Because I explain you only diagrammic approach, but of course there are different approaches to Jones polynomials, so maybe it can be interesting. Yeah. Of course, we can think also about graphs and nodes in another three-dimensional manifolds. But it's only in the future. Because for this result, we spent a lot of papers and computations. Maybe we need to use some AI approach. Thank you. Thank you.
Is there an analog of Alexander polynomial for spatial graphs?
Yes, there's some definition, but in the case of spatial graphs, people, okay, Alexander polynomial is very classical, it has different properties. And for example, last year with my students, we tried to find a good generalization of Alexander polynomial for graphs. But the problem is that you generalize some properties, but other properties don't hold. And really this equation under discussion among many people. There are few generalizations of Alexander polynomial for graphs, and it is not clear which to use. So you get some properties, but you lose another one, unfortunately. There's some construction, and there's construction of Alexander module for graphs. It was done by Little and many years ago. It depends on what kind of properties you want to generalize.
Okay, if there are no further questions, let us thank speaker again.
Thank you very much.
We have coffee break as usual on the first floor.